Entonces, bueno, lo presento a David. ¿Sí? David hizo su doctorado en la Universidad de California en Berkeley, bajo la dirección de Donald Saracen. Después hizo una postdoc en la Universidad de Purdue con Nosh Bauer, con quien trabajó un montón de artículos que yo conozco. Después pasó 19 años en la Trinity College de Connecticut, hasta que hace 5 años que se mudó a la Universidad de Alabama, donde es profesor y además es el jefe del Departamento de Matemática. Obviamente le interesan como ya van a ver en el título, las desigualdades con pesos, la extrapolación, los espacios frente variable y las aplicaciones que tienen el análisis armónico a las ecuaciones diferenciales. ¿Sí? Bueno, entonces, David, cuando quieras, puedes compartir pantalla y comenzar tu charla. David, you can start.
I almost understood that introduction. So first of all, thank you all. Thank you especially to Estefania for this wonderful invitation. My friend Christian Rios has been telling me for 15 years I have to go to Santa Fe. I'm almost in Santa Fe now, so let me share my screen since none of you want to sit and look at me. Vale. Okay, so again, also let me apologize for having to give this talk in English. As many of you heard, me llamo Cruz-Uribe, pero hablo solo un poco de español. My apologies to Carlos Perez, who's been trying to convince me to learn to speak Spanish for 25 years now, to no avail. Okay, so my talk is on norm inequalities for linear and multilinear singular integrals on weighted and variable exponent Hardy spaces. Estefania asked for a very general talk, and so there are some real experts in the audience, so I asked their forbearance if I gloss over things or say some things that they already know. Everything I'm going to say today is joint work with Cade Moen, who's also on the faculty at the University of Alabama, and Han Nguyen, who is a student of Lucas Grafakos and was a postdoc for 3 years at Alabama. So let me start with something simple. I want to talk about the linear case before I go on and talk about bilinear inequalities, which are the main result I want to talk about. So let's begin with something very simple, the convolution type singular integral, which is just a present value integral of your function against some nice kernel k. What I want to emphasize, though, is throughout this talk, we're going to be assuming more regularity on the kernels than you usually see. So for example, if this was the Hilbert transform in one dimension, the kernel is just 1 over x, you would see this kind of regularity on the derivatives. So we're taking the derivatives here in the x variable. And this constant here, capital N, will always refer to the regularity of the kernel. And that's going to play a very important part in all the results I'm talking about. So in defining these, we assume they're bounded on L2. The L2 bounds plus the kernel regularity means they're bounded on all the LP spaces, P between 1 and infinity. And we want to embed these now and look at when P is less than 1. The Lebesgue spaces are not, when P is less than 1, are not the natural place to look. So instead, we want to talk about the Hardy spaces, which we'll define using Stein's grand maximal operator. So here we just take a maximal operator, which is defined by convolving against some kernel function phi. Phi just lies in some Schwartz class of Schwartz functions. N sub 0 is some large constant that we will fix once and ignore. Just think of it as a very, very large number to make sure that all possible definitions of the Hardy spaces agree with one another. And then the classic result from Pfefferman and Stein in 1972 is that if T is a convolution type singular integral operator, and if you fix P again between 0 and 1, and fix your regularity large, so this expression is 1 over P, which could be very, very large, less than 1 times N, take the greatest integer, add 1. So if N is bigger than that, if you have that much regularity, then you're bounded on the Hardy spaces, and you're bounded from HP into HP. Okay, this is a classic result. But starting in the 70s, we moved away from just convolution operators to the more general Calderon-Zygmunt operators, where you're now integrating against a non-convolution kernel, K of two variables, X and Y, and we assume that the kernel has some natural decay and that it satisfies some kind of regularity, which is a little bit weaker than being C1 in each variable with decay. And then again, we assume it's bounded on L2. And again, with these hypotheses, these operators are bounded on all the LP spaces. So the question is what do you have to assume for these operators to be bounded on the Hardy spaces? So there's a result due to Alvarez and Millman in 1986. I snuck my own name in here because we proved a slightly different version of this result in 1918. And so they showed that, again, if you impose a regularity condition on the kernel, so written here is the regularity on the differences of the derivatives, and again, we have to go to some very large constant n+1. And then we have the following condition, which is a vanishing moment condition on the operator T when applied to an atom. So an atom is just some function which is supported locally, say in a ball or a cube, has a large number of vanishing moments. And so if T applied to those atoms again has vanishing moments, we have the right kind of thing. Any convolution singular integral operator satisfies this condition. And so then the theorem is almost exactly the same now as the result of Pfefferman and Stein. So again, this was the condition for Pfefferman and Stein. Here we have the same condition where n, big N, again, is the regularity on the kernel. And then this non-convolution operator maps HP into HP. Okay. So let me move to the case I want to consider now, which are bilinear singular integrals. We could write these down as M linear operators, but for simplicity, I'm only going to talk about the bilinear case. Everything I say extends to the M linear case with suitable adjustment. So in the bilinear case, we have a kernel K and an integral operator where we have the functions both F, well, they should have been F1 and F2 here. Sorry, typo. And so you apply the operator to the two functions, and this has to be defined in some present value or distribution sense, because all we assume on the kernel is that it satisfies, again, some kind of decay condition on its derivatives. And we also have to assume that it's bounded on some product of LP spaces. So for example, it could be bounded from L2 cross L2 into L1. Okay. And so these are well known to be bounded on the Hardy spaces, as long as, in this case, if Q1 and Q2 are bounded between 1 and infinity, then these hypotheses are sufficient to have T be bounded on any of these product spaces. We want to ask, is there a bilinear result? And so Grafakos and Colton back in 2001 showed that if we have an operator like this, and again, almost exactly the same assumption as in the Pfefferman-Stein theorem, if you have enough regularity on your kernel, then T is going to be bounded from HP1 cross HP2. And notice here we write LP, not HP, but LP. There's a version of this result which is true if we put HP here, and it's more complicated. And what you have to do is you have to increase N substantially. So I don't want to talk about that. I want to concentrate on this simpler case where the condition looks so much like the condition in the classical linear result of Pfefferman and Stein. Okay. So the problem that Cabe and Han Nguyen and I were interested in was, could we generalize this bilinear theorem to different kinds of function spaces? And the two spaces we were interested in were Hardy spaces defined with weights and the so-called variable exponent Hardy spaces. And I will define those for those of you who aren't familiar with variable exponent spaces. So let me talk about the weighted spaces first. And of course, Santa Fe, everyone knows what a weight is, but let me just say these things anyway. A weight will just always be a non-negative locally integrable function. The simplest example, of course, would be a power function, x raised to some power a, chosen appropriately. And we just define a new weighted Banach function space by replacing the Lebesgue measure by w dx. Okay, and these are well-known spaces. And the grandfather condition in any of these spaces is due to Ben Muckenhaupt. The AP condition, which basically says that the average of W, so if you see this bar, this means divide out by the Lebesgue measure of Q. The average of W multiplied by roughly the average of 1 over W, this product is uniformly bounded. Or when P is equal to 1, the average of W is bounded above by the essential infimum of W. So these weights have a lot of structure, and I'm not going to talk a lot about that. But here are some basic properties that we need to have in mind, that these classes are nested. So if P is between 1 and less than Q, less than infinity, then A1 is contained in AP is contained in AQ. So what this means is that if I have a weight in AP, I should be able to find a quantity which is the infimum of all the P's of the AP classes it belongs to. So I'm going to use this notation through the remainder of the talk. So R sub W for a weight W just means this infimum. And then since they're nested, it makes perfectly good sense to talk about the union of all of these classes. And we'll just call that A infinity. Okay. These weights are intimately connected with the Hardy-Littlewood maximal operator, which is just the supremum over averages on cubes. And we have the famous theorem of Muckenhaupt, which says that the AP condition is equivalent to the maximal operator being bounded on this weighted space, LP of W. Okay, and this theorem plays a big role in what I'm going to say going forward. Okay, weighted Hardy spaces go back to first Pepe Garcia Cuerva in around 1980, and then the book by Stromberg and Torchinsky in the early 1980s. And so what we do is we fix P. Now, unlike the classical case, we're going to let P between anywhere between 0 and infinity. W will just lie in some A infinity class. And we'll just say that a function or a distribution lies in the weighted Hardy space HP of W if, when you again apply the Stein's grand maximal operator, you land in LP of W. And again, N0 is just some big constant, which now depends on the weight, and we just sort of pick it and forget about it. Okay. Now, it's important to notice that if P is bigger than 1 and W is an AP, then the Hardy space HPW just becomes the Lebesgue space LPW. And that's because the grand maximal operator is bounded pointwise by the Hardy-Littlewood maximal operator. But, and this is very important, you can have P bigger than 1, but if W is not an AP, this equality is not true. So when we're studying these spaces in the weighted setting, we have to think about them for the whole range of P's. You cannot just restrict yourself to P less than 1. Okay. Now I want to talk about variable exponents, and the intuition here is very simple. If you think of the LP space, you make the exponent to be a constant P. The variable Lebesgue space says, let's replace the constant exponent P by a function P punto. Okay, so we're just going to let P sub 0 be the set of all functions P punto, which map Rn and take values anywhere between 0 and infinity. Okay, and a natural question we can ask is, what's the oscillation of this function? So P minus will just be the essential infimum of P punto. P plus will be the essential supremum. And we're usually going to assume that those P minus is greater than 0 and P plus is less than infinity. You don't have to, but in a lot of settings, that's a natural assumption. Now, we can take any measurable function, and as a theory of Banach function spaces, it makes perfectly good sense to do so. But to do harmonic analysis, some simple examples show you need some kind of regularity on the exponent P. And the default assumption is log Holder continuity. So the first condition right here is a local condition, which just says that the difference between P of X and P of Y decays like 1 over the log. And the second condition is log Holder continuity at infinity. So p of x decays uniformly to a constant p infinity in all directions. And the rate of decay is, again, just 1 over the log of your distance from the origin. Okay, so together we say that the function f is, or excuse me, that should be a p. We say that the exponent p is log Holder continuous if these both hold. Okay, so now we want to define a variable Lebesgue space. So this is the space which is going to replace LP. We can't just take the norm, so we could write f of x to the power of p of x, integrate it, but we can't put 1 over p of x on the outside. So we use this idea called the Luxembourg norm, and we take this infimum over all of these lambdas, which make this quantity less than 1. Okay. If p is constant, it's easy to see that this immediately reduces to the Lebesgue space norm. So with equality of norms in the constant exponent case, LP punto is just LP. So these spaces really are a natural generalization of the Lebesgue spaces. Okay. And so an old question, which is the question that first got me interested in these, is what do you have to assume on an exponent for the Hardy-Littlewood maximal operator to be bounded? And these two essential conditions, one is you must have p minus greater than 1. So just like the Hardy-Littlewood maximal operator is not bounded on L1, if you have a variable Lebesgue space where the exponent's allowed to drop down and be equal to 1 or get arbitrarily close to 1, the maximal operator fails to be bounded. And then you need some kind of regularity condition, and a sufficient condition is to assume log Holder continuity. It's a long-standing open question to really understand what you can replace log Holder continuity by. I'm not going to get into that. I just mentioned that because I've been worried about it for 10 years and I'm still stuck on that question. Okay, so how do we define a variable Hardy space? So this goes back to a paper with my postdoc, Daniel Long, when I was still at Trinity College, and independently to 2 Japanese mathematicians, Nakai and Solano. And we, again, just replace the variable Lebesgue, the classical Lebesgue space with the variable Lebesgue space, and use the Stein definition. So f will be an HP punto if we take the Stein grand maximal function of f and it lands in the variable Lebesgue space, LP punto. And again, n0 is just some large constant. We fix it and forget it. Okay. So again, by the boundedness of the maximal operator, if p minus is bigger than 1, and we assume log Holder continuity on the exponent, then HP punto and LP punto are the same. So we would be back in sort of the Lebesgue space case. But again, because we have a variable exponent, we're going to be most interested in the case where p minus is less than 1. So in other words, your exponent is going to be taking values below 1 in some places and possibly bigger than 1 in other places in Rn. So you can think of this as locally it's behaving like a Hardy space in some places and very locally behaving like a Lebesgue space in other places. Okay, and again, just for technical reasons, I'm not going to let p minus sink all the way to 0. I'm going to keep p plus bounded, so the exponent has a finite, possibly very large interval it can oscillate in, and we'll control the oscillation to the extent we require it to be log Holder continuous. So here's the big result that I want to talk about. This is due to myself, Kate Moen, Han Nguyen, generalizing work that Han did in his thesis with Lucas Grafakos. So let T be a bilinear singular integral operator. We'll fix 3 values, P, P1, and P2. P1 and P2 can be anywhere between 0 and infinity, and we define 1 over P by the classic 1 over P equals 1 over P1 plus 1 over P2. Then we're going to fix 2 weights, W1 and W2. They're both going to be an A infinity. And then we're going to define a new weight, W, which is basically the geometric mean of W1 and W2. So sorry, there's a mistake on the slide there. That should be W1 here and W2 here. And now we have, the condition is we should somehow control the regularity of our operator. And so we have a more complicated expression than in the classical theorem of Pfefferman and Stein, or Grafakos and Colton in the unweighted case. And the reason for that is the weights W1 and W2 are not coupled to one another. We make no assumptions that one of them is comparable in any way to the other one. And so therefore we have to take into account that we have very different regularities on the space HP1 and HP2. And so our regularity has to reflect that. And so what we do is we have this more complicated expression. In the unweighted case, we would take this to be 1 and this to be 1. And the quantity you get, you can play with this with a pencil, is a little bit bigger than the quantity in the theorem of Grafakos and Colton, unless P1 and P2 are equal to one another, in which case this would be the same quantity. And so with this amount of regularity on the kernel of the operator, then the bilinear singular integral operator T maps HP1 cross HP2 into LP. Okay, so that's the weighted theorem. The variable exponent space theorem looks almost exactly the same. So we fix 3 exponents, P punto, P1 punto, P2 punto, related by this expression, which means this equality holds pointwise almost everywhere. And then for the regularity on n, it depends on the smallest possible value that P1 takes and the smallest possible value that P2 takes. But otherwise is, again, very similar to this quantity right here that we get in the weighted estimates. Okay, and again, with this much regularity on the kernel, the bilinear operator T maps HP1 punto cross HP2 punto into LP punto. Okay. Excuse me. Okay, so these then are our 2 main results. We have a weighted estimate and a variable exponent estimate. And so what I want to do first is I want to prove the variable exponent result, because that has a very simple result if we assume the weighted estimate. Okay, and to get here, we're going to use the miracle of Rubio-de Francia extrapolation. I started calling it a miracle a few years ago when I was giving a talk in Germany, and I was trying to explain to a German why some result was true, and I finally just had to say, it's a miracle. Okay, and it really does seem to be a miracle. And one of the things I want to emphasize in this talk is the central role that Rubio-de Francia extrapolation plays in our proofs. Some of our lemmas can be proved without it. Matter of fact, I suspect all of them can be proved without it. But the proof is so much easier using some form of extrapolation that this is really the way to think about these kinds of problems, I think, going forward. If you have some kind of estimate, see if you can prove a more general version of it and then extrapolate. So the version of extrapolation I'm going to use is due to myself and Virginia Naibo. Shout out to Virginia, you were here, so you get to see me talk about you. And basically it says is if you have any kind of operator T defined on a pair of Hardy spaces mapping into any LP space with very strong assumptions on the weights. So instead of A infinity like in our theorem, you only have to have this hold if the weights are in A1. And then, whoops, excuse me. For any pair of Hardy spaces, HQ1 punto, HQ2 punto, as long as the lower bound on Q1 and Q2 are bounded below by P1 and P2, then you can extrapolate and automatically prove the same inequality on a variable Lebesgue space. So since Carlos and Chema Martel and I and Alberto Fiorenza came up with this, this has been the biggest tool for proving results in the variable exponent spaces. Is it basically boils down to proving the corresponding weighted norm inequalities. Okay. Now, very often you need to prove a very specific kind of extrapolation theorem to make this work. So key to a lot of the things that I'm going to talk about are some variations on the classical Rubio-de extrapolation. But the ideas that Carlos and Chema and I laid out in our book seem to work again and again and again. If you need an extrapolation theorem, the tools are there to prove it. Okay, so with extrapolation then, this means that this theorem for variable exponent Hardy spaces will follow immediately if we can prove the weighted estimate. So for the rest of my talk, I just want to talk about what's going on in this weighted theorem. Okay, so the proof depends on 5 pieces, okay, cleverly assembled. First, we need not simply an atomic decomposition theorem with weights, we need a finite atomic decomposition. And I'll talk a little bit more about why we need that. The next step in any argument is what I call a local and global decomposition. So if you pass to an atomic decomposition, you can basically think of your function as put together from these atoms. Each atom is supported on a cube or a ball. And so in our proof, what we have to do is we have to estimate our operator applied to just a single atom. And then the natural thing to do is to consider it locally close to the support of the atom and then far away. The technical problem that comes up in a bilinear estimate, however, is you'll have your operator applied not to a single atom, but 2 atoms. And so then local and global becomes more complicated because you basically have to treat 3 cases. The supports of the 2 atoms are very close together, and you're close to both of them. The supports of the atoms are very far apart, and you're close to the support of one and far away from the support of the other. And the third and easiest case is you're very far away from the supports of both atoms. Okay, so that, particularly in the multilinear setting, leads to a lot of technical problems. But the basic idea is this: you want to split things up so you're working close to an atom or far away from an atom. Then you use your regularity to get pointwise kernel estimates, and these generally are most useful when you're far away from the support of an atom. Okay. Then, particularly when you're estimating locally, you need vector-valued inequalities. Okay, now these have been around in the study of Hardy spaces for a long time. They date back to Pfefferman and Stein in the 1970s. We want to look at them at a slightly different way and think of all these vector-valued inequalities as being a consequence of Rubio-de Francia extrapolation. Okay, so rather than try and work through the proof of the bilinear theorem, I want to illustrate all of these techniques in a simpler setting. Okay, and so I just want to go back to the linear case. Okay, so I mentioned the unweighted linear case for these operators with the paper of Alvarez and Millman. Here I want to talk about the weighted result, which is due independently to myself, Cabe Moen, and Han Nguyen, and also Jared Hart, Rodolfo's student, and Oliveira in a separate paper in 2017. I'm going to state the result in the form that we proved it. They gave a very different proof and give a very different statement, which I think is more or less equivalent to what we proved, though I think they require more regularity on the kernel. But in essence, we're trying to do the same things, and so I want to give them full credit. So what's the theorem? Again, we're going to be working in some Hardy space, and so we'll fix P between 0 and infinity and a weight in A infinity. T is going to be any Calderon-Zygmunt singular integral, and we impose this kind of regularity condition on the kernel. And again, capital N will measure how many derivatives we need regularity for. We again have to assume this vanishing moment condition on the kernels. And this is not an unnatural condition. As I said, it holds for any convolution type operator. And you can show in certain cases that it's actually necessary for a Hardy space estimate to hold. And then we can prove this estimate. So if the regularity is greater than n times r sub w over p minus 1, then T maps HP of W to HP of W. So this result is really a full generalization of Pfefferman-Stein to the weighted Hardy spaces, but we like this result because it's not just convolution singular integral operators, but the more delicate problem of any Calderon-Zygmunt singular integral operator. So I want to walk through the proof of this theorem, and the proof has the same 5 steps, okay? And so you can see in this simpler setting how these things play out, okay? So first, we want a finite atomic decomposition. Now, any Hardy space, and it's classical, goes back to Stromberg and Torchinsky, that even a weighted Hardy space, you can get an atomic decomposition. But that just means that you can write every func f in your Hardy space as an infinite sum or infinite linear combination of atoms, okay? We want to avoid that, and we want to talk about just finite sums of atoms, okay? And the key to proving a finite atomic decomposition is to prove that there's a dense set in your Hardy space which consists of finite sums of atoms, and then you can find such an atomic decomposition, because they're not unique, such that the Hardy space norm of F is equivalent to this expression. Now, if you're familiar with atomic decompositions in the unweighted case, this is going to look unfamiliar, because there it usually only depends on the coefficients, the lambda sub i's. Here, we need an expression that reflects the lack of homogeneity in a weighted space. So what we do is we multiply the lambda sub i's by characteristic functions of the cubes qi, which is the support of the atoms, and then take the sum of those and take the Hardy space norm. Okay, and this turns out to be the right way to think about the atomic decomposition norm in a weighted or variable exponent space. And now the reason we want the finite atomic decomposition is this lets us pass a singular integral operator through the sum without worrying about convergence conditions. Okay, now in the linear case, this is well worked out. Garcia Cuerva and Rubio de Francia have this for convolution operators in their book. It's worked out other places for the non-convolution operators, that this passing through an infinite sum makes sense. This is a much harder question in the bilinear case. And indeed, the paper by Grafakos and Colton, they assumed that in the bilinear case, you could pass through an infinite sum. Grafakos and one of his students came back several years later and had to publish an addendum where they work out the conditions under which this is possible. Okay, so for our purposes, we want to make sure that we can prove a finite atomic decomposition. And it's not that bad. You can follow the ideas of, I believe it was Sojgren in the unweighted case, and in the weighted Hardy spaces, prove one of these. And they also exist in the variable Lebesgue spaces. Okay. We also want to use an equivalent norm, and this is again why we fix that constant n0 at the beginning of the proof to be something very, very large. That lets us replace the grand maximal function of Stein by a single maximal function where you convolve against some nice kernel. And for our purposes, we have to take it to be C infinity with compact support, supported in the ball. Okay. But once we do that, then this norm right here will be equivalent to the Hardy space norm. All right, so then the key is what I call this local and global decomposition. So I want to find the Hardy space norm of t applied to our function f in this weighted Hardy space. And so that's equivalent to applying this radial maximal function to t of f and looking at LP of w. And now I'm going to split things up. And this should be a curly less than or equal to, because if p is less than 1, we'll pick up a constant. But the basic idea is we replace t of f by t applied to the linear combination of atoms, because we're going to fix f in this dense subspace. And then we split the sum up. We use the sublinearity of m sub phi. And then we divide the domain up. If the support of AI is QI, QI star means we just blow Q up I, say, square root of n times, or maybe 10 times the square root of n times, just some big constant, some big cube, same center as q sub I. So we'll look at this object locally and then very far away. And so when I talk about the local and the global pieces, this is what I mean. I mean, looking at the pieces where the atoms, where you're far away from the support of the atoms and where you're close to the support of the atoms. Again, if we were doing this in the bilinear case, I would have to worry about a mixed term where you're close to the support of one atom and far away from the support of another atom. But a lot of the tools that we use here still work. Okay, so let's deal with the global piece first. And the first is this lemma, which I've never seen written down exactly in the form I wanted it, but it's in Stein, it's in other places more or less. And so the idea is that if you apply a singular integral operator to an atom and then apply the radial maximal function, and if you're far away from the support of the atom, then you get something which looks like the maximal operator applied just to the characteristic function of the cube, which is the support of the atom, with an exponent which grows depending on the regularity of n. And so if you think about what this means, this maximal function is equal to 1 on the cube and then decays like 1 over your distance from the cube. And so then this, basically, if big N is much, much larger, then this is going to be very, very large. So this is an object which decays very, very quickly as you move away from the origin. So it's a very, very nicely behaved function. Okay. Then to estimate this, we're going to use a vector valued inequality. In the unweighted case, this is due to Pfefferman and Stein. In the weighted case, to Anderson and John. And it just says that if you have the maximal operator applied to a sequence of functions f sub I, combined with the little L sub R norm, and then in the weighted space LP of W, you can peel the maximal operator off. Okay? So what I want to stress here is, if you go back to the original proof of either Pfefferman and Stein or Anderson and John in the weighted case, this requires a very delicate analysis. Okay? It's not a trivial proof, but it is absolutely free as a consequence of Rubio-Differential extrapolation. Okay? So if you have a scalar inequality with weights for any operator, you automatically have a vector valued inequality like this one. Okay, and I think that's one of the free things that you get from extrapolation that makes it so powerful. Okay, so now let's do our global estimate. All right, so remember our weight was an A infinity, but we chose N. If you go back far enough here, this is where this regularity condition comes in. Notice now the regularity condition says that N is somehow large in comparison to this quantity R sub W, which tells you sort of the minimum P for which our weight is going to be in one of the AP classes. And so in particular, what that condition says is that if you take tau to be this exponent, little n plus big N plus 1 over n, and again, that's the exponent that shows up here in the pointwise inequality. With that assumption, W is in this class A tau P. And we're going to use that because that's going to give us the boundedness of the maximal operator. So if we look at the global piece, and then we apply the pointwise estimate, we get it bounded by this sum, where we get the maximal operator applied to these cubes, q raised to the power tau. Well, now I'm just going to raise everything to the power 1 over tau, and then pull the tau out. So this becomes an inequality now not in LP, but in LP times tau. So now we have rewritten everything, and we've got a vector valued inequality for the maximal operator on a space where the maximal operator is bounded. And therefore, we can apply the vector valued inequality and throw away the maximal operator. And so we get this. We undo that power tau, and we get this quantity. And remember, what is this quantity? This is equivalent to the Hardy space norm of the function f. This is the atomic decomposition norm of f. which is equivalent to the Hardy space norm of F. Okay, so there we are. Very, very quickly, we estimate the global piece. But in almost any kind of estimate involving singular integral operator, if you're far away from the support, things are easier. So let's worry about now what's going to happen locally. Well, the amazing thing is the proof is almost as simple. We need another inequality. A version of this is due to Grafakos and Colton in their 2001 paper. In our paper, we generalized it. And so let's look at what it says. It says, suppose you have a sequence of functions gk, each one supported in a cube qk. And key here is we are not assuming that the cubes qk have disjoint supports. So this sum here is like a sum of atoms. You want to think of it as like a sum of atoms. These things can overlap and pile up as much as you want. And so then we put a weighted condition on W. We say that W satisfies some reverse Holder inequality. Okay. And that's okay, because if a weight W is an A infinity, it's going to satisfy some reverse Holder inequality. And notice Q is free. We can take Q as large as we want. Then we take Q over P, which is very, very large. We take the dual exponent. So as long as it satisfies a reverse Holder inequality with a conceivably very, very small estimate, we can replace the sum of the GKs by, there's a missing summation symbol here, by the sum of the averages of the GKs in LQ. So again, sorry, there should be a summation here, but we're summing the average of the GKs. And notice now, this is an unweighted average of GK. Okay, and then we stick in a characteristic function of the cubes QK here. Okay, this was proved by Grafakos and Colton when Q is equal to 1 and P is strictly less than 1. And I want to emphasize that their proof is extremely difficult. And again, the difficulty comes from the fact that these cubes QK are not disjoint. Okay, but it turns out, and this was an observation of Cade Moen, was if Q is bigger than 1 and P is less than Q, this is very easy to prove even with weights in a reverse Holder class, and then you can just apply extrapolation. Okay, so if you choose very particular exponents, you can make this work, and then you can extrapolate to all P. This is due to a version of extrapolation we call reverse Holder extrapolation, which is more or less due to me, Cade Moen, and Tess Anderson. And Chema Martel and one of his students proved something like this very similar independently. So again, you can think of this as a vector valued inequality, because we're going to use this for a finite sequence, but clearly this also could hold for an infinite sequence. So this is some kind of vector valued inequality, which again, the key idea I want you to take away is we prove the vector valued inequality by proving one special case and then proving it using extrapolation. Okay, so now with this in hand, let's do the local piece. Okay, so remember the local piece is just m phi t applied to the a sub i's multiplied by the characteristic function. So if we apply the lemma, well, since w is an a infinity, we can find a q really large so that w satisfies this reverse Holder inequality. So we just pick up some LQ. It's going to matter, but not as much as you might think. And we replace this, the sum of these functions, by the sum of the averages of these functions on an unweighted Lebesgue space. Well, we're on an unweighted Lebesgue space. We can pull the average out and ignore that, so we just have the LQ norm of this function. Both of these functions, operators, m sub phi and t, are bounded on LQ. So we can throw them away, literally. We pick up a constant here that depends on Q and a couple of other things, but they're gone. And now we just have an atom, okay? Atoms are L infinity functions bounded by 1, okay? So this whole average right here is at most 1, so it's gone. Okay, and now we're basically done, and we're going to reduce it to what the estimate we did for the global case. Because let's look at this. This is a characteristic function of a cube. Okay. But if you think about how, I'm going to cover up that exponent tau, if we take the maximal function of the smaller interior cube, q sub I, well, that's going to be bounded below by some constant which only depends on how big we dilated to get qi star. So point-wise, this characteristic function is dominated by a constant multiple of this maximal function. And for free, because this is either equal to 1 or is a nicely decaying function, we can stick any exponent tau we want on it. Okay? And in particular, we choose tau as we did in the global case. So now this term right here is exactly the term we already estimated in the global case. And that's controlled by the Hardy space norm of the function f. So we've estimated the global piece. We've reduced the local estimate to the same estimate as in the global case. And so we're done. And that proves this inequality. Okay, so I really like this proof because even in the linear case, even in the unweighted linear case, it gives a very clean proof of the boundedness of singular integrals on the Hardy spaces. And I think that with all the tools that it uses, I mean, yes, you have to invoke the finite atomic decomposition, which is work. And you do need to prove a lot of extrapolation theorems. But once those are in place, you get a very, very clean proof. Okay. And it extends immediately to the weighted case. It extends to the variable exponent case. You can get the variable exponent case either directly, because you can make the same proof I just showed you work, or you just extrapolate from the weighted case. So with these tools, we proved the multilinear weighted theorem for singular integral operators. We can prove some other results, and I just want to mention these. I don't want to go into any details. We can also have, instead of mapping from the cross product of Hardy spaces into a Lebesgue space, we can also get results mapping into Hardy spaces. And the key idea is you just need more regularity on the kernel. Okay. We can get away from Calderon-Zygmunt operators and get to multilinear multipliers, and we have some very weak regularity conditions which generalize, say, the Horn-Mander condition. Okay, and we can also generalize these to these so-called multilinear fractional singular integral operators. Okay, so these are all the kinds of results that we proved, and you can find these in a series of papers by myself, Cabe Moen, and Han Nguyen. They're all on the archive. Most of them have been published by now. Okay. Let me talk about some open questions. Okay. We would like to improve the bilinear theorem because if you go back to the statement of that theorem, I'm going to make you all incredibly dizzy for a moment. Okay, here to get n, to get the regularity, we have to assume a uniform condition on n that depends on somehow the regularity of the weight W1 for the first component and the regularity of the weight W2 in the second component. But if you stare long enough at the definition of the Calderon-Zygmunt operator, there should be, the bilinearity isn't being respected here. So somehow, if this is the worst space, then we should need more regularity in the variables that correspond to this function, and perhaps not as much regularity as would correspond to this function. Okay, and so what we're asking for, and I could make this precise, is can we improve the bilinear, or more properly the multilinear theorem, by getting different regularity in the kernel in each variable? Okay, so instead of a single assumption n, we would have an assumption n1 and n2 on each variable, and somehow have different regularities depending on the weights on each of those. Another thing which I think is really possible is to extend the linear theory to Hardy spaces defined over other kinds of function spaces. Okay, so what do I mean by that? Well, we have the definition of a Hardy space in terms of, say, the grand maximal operator. Okay, well, and then that's defined with respect to a Lebesgue space, a weighted Lebesgue space, a variable Lebesgue space. Well, what if we put a different kind of Banach function space down there? For example, an Orlich space or an Musilak-Orlich space, one of the generalized Orlich spaces. Could we use these ideas to prove boundedness of Calderon-Zygmunt operators on these more general kinds of Hardy spaces? I think the answer is yes, and in our paper we sketched some notes at the very end. And so I threw it out there because I didn't have a student who was interested in working on this, but I think it's a really interesting question if you're interested in harmonic analysis on different kinds of function spaces. And then another problem would be to extend the linear theory or even the bilinear theory to other kinds of Hardy spaces. So what do I mean by this? Well, rather than looking at the classical Hardy space, there are definitions of Hardy spaces that have shown up in the past 15 years or so that are configured to different kinds of kernels. So if you think of the Hardy space as somehow being intimately related to the semigroup defined by the Laplacian, if you have some kind of other elliptic operator or degenerate elliptic operator that has a semigroup associated with it, that leads naturally to a Hardy space. Does this theory extend to these Hardy spaces? Can we make these techniques work in those settings? I think that's a wide open question. I've toyed with it, but haven't got anywhere with it. And I'd be really interested in seeing results in that direction. So I've lost track of the time, but this is my last slide. So let me say thank you, muchas gracias. And since I'm from the University of Alabama, I have to say roll tide. Thank you.
Muchas gracias, David. ¿Alguien tiene preguntas? Después aplaudimos al final. Si alguna las quiere hacer en español, puedo intentar traducir. Pueden activar sus micrófonos y cámaras si quieren. O levantar la mano, lo que deseen. ¿Alguien?
¿No hay preguntas?
No.
Parece que no.
Ok, vale.
¿Nadie? ¿Comentarios? ¿Algo? Bueno, por mi parte, David, thank you very much. Very nice talk, very clear as usual. I don't know if anyone wants to ask something now. If not, aplaudimos todos. Si quieren, prendan la cámara. Y lo aplaudimos,
Ricardo,
por favor. Ricardo, bueno.
Ricardo. Ay, no sé,
Ricardo. No se escucha, Ricardo, creo.
His microphone is muted.
Yes. A ver,
Está con el
revisarlo.
micrófono apagado.
Ricardo,
Ahora sí, Ricardo.
Nice to see you, David. Thank you for the talk.
Yeah,
no,
thank you.
My question is not on the bilinear, but on the linear case. If there are for HP for results without assuming smoothness of the kernel, because I know in LP this is possible as in the old Calderon-Zygmunt condition with the homogeneity and things like that. This is true also for HP, and the other question if this is true for weights.
I think you need, at least I've always believed that you need that regularity on the kernel.
You say this is really needed. This is a necessary condition. It's possible to prove that?
I've never seen it proved. I've just always seen it assumed. And when I ask people, they say, yeah, you need it. So does need mean necesario,
Yeah.
or simply it's the easy, convenient thing to prove in this case?
Yeah,
I mean, you can weaken regularity because if you treat it as a multiplier, so at least in the convolution case, if you treat it as a multiplier, you can considerably reduce the regularity, but you still need something.
But I think if you think of a convolution, then it's essentially self-adjoint, and so the adjoint will be bounded on Lipschitz spaces, which are the dual of Hardy spaces. And there, I think one can probably show that it's necessary to have a regularity on the kernel to get a smooth function. Right?
But this is true because the HP are not Banach spaces, so I don't think if you can prove things by duality. I have thought on that once and I was not able. I mean, you are thinking in using that kind of duality argument.
Yeah, for unweighted space, that's true, right? The dual of Hardy space are.
Well,
Yeah, this is true, but it's not the opposite way. I mean, the Hardy space is not the dual of the. So you cannot. Well, I don't know. It's something.
No, but what I'm saying is, if you have an operator that map HP into HP, then the adjoint maps the corresponding Lipschitz space into the corresponding Lipschitz space.
Okay, this is true. Yeah.
And so if it's a convolution, the regularity on both variables is the same. And I don't know it's a fact, but I think one can probably show that if you need to map a smooth function into a smooth function, you need to have some regularity on the kernel.
Okay, I understand. Yes, I understand. Yeah. Thank you.
Okay.
thank you, Rodolfo. I saw Silvina hitting her mate. I realized I forgot to bring my bombilla, my mate.
I'm drinking mate cocido.
Sin bombilla. Sin bombilla.
¿Alguna otra pregunta o comentario?
If the range is, in the case bilineal, the range is possible to another Hardy space? The range.
Yeah, so in the theorems where I write LP spaces, weighted or variable, we can prove these results with also a Hardy space for the range, but the price is more regularity on the kernel.
More. Oh, okay. Yes.
What you need is intuitively, you need enough regularity to remove the maximal operator and not lose anything.
Okay. Yes. Very good.
¿Alguien más?
David, I have a question.
Virginia.
Yes. In the extrapolation theorem, you state that you stated it using HP spaces, but we prove it for Lebesgue spaces. So are you saying that it's straightforward to go to the Hardy spaces in that case?
Yes, again, it's the miracle of extrapolation because you don't prove it for an operator, you prove it for pairs of functions.
Correct.
And so what your operator would be the maximal operator applied to your operator.
Okay, I
So
see
then
that.
the Hardy space norm becomes
Correct.
the Lebesgue space norm.
Perfect.
¿Alguien más? Bueno, entonces agradecemos a David, aplaudimos. Si quieren activar sus micrófonos. Muchas gracias, David.
Ahí está. Thank you, David.
Gracias, muchas gracias a todos.
Gracias.
David.
Someday in Santa Fe.
You have to come.
All right.
Next year in Santa Fe.
Hasta
Thank you
luego.
very
Nos
much.
vemos.
See you.
Bye.
Bye.
Gracias, chao.
Bye,
Muchas
everyone.
gracias.
Bye.
Bye.
Thank you again, Estefanía.
Thank you.
Estefanía,
Thank
bárbaro
you.
todo.
Thank
Chao.
you.
Muy bien. Chao, David.
Chao, bye.
Bueno, nos vemos la próxima.
Eso,
Adiós.
nos encontramos.